Then we continue with the next presentation. It's given by Stingelins. Simon is also one of the one-digit NGSolve users. Club numbers. Simon used at the beginning NGSolve a lot for multiphysics simulation when he was in a company. Simon switched to University of Applied Sciences in Zurich. Now using mainly NGSolve in teaching finite elements, and he's doing a lot of projects with his students. No from industrial experience. Simon was also the one who showed me Jupyter books, and that they are very useful for communication and for teaching, and you present what you are doing in your notebooks and keep it online and keep it accessible. So I think I have to continue a bit speaking, but since as long as Simon is starting up the computer.
So, my talk would not be in the same matter as the other ones. So, because I'm have to focus on teaching, as Joachim mentioned, I have a module, we call it, at the Fachhochschule or Applied University of Applied Science. So I'm from Switzerland, and there we have this model that we have these universities of applied science behind the technical university. It's only one, it's the ETH, and so we have the focus on the education of engineers for, let's say, for the praxis. So I want to show you this course, the concept of this course and the material I use there, and in special these projects I have for the exam, because I don't want to give the student an exam because otherwise they have to learn much, and I think they should see at the end nice pictures, because engineers love like nice pictures, as I do as well. So, and here comes of course NGSolve in the play, so we are able to make many interesting projects. Then I have a part with Jupyter book. Jupyter book, I think it's a very interesting model to give students material to be able to compute everything. And here I show a markdown file and a Jupyter notebook. So let's start with this higher analysis and numerics I called. So the students are from the School of Engineering, and typically from computer science, mechanical engineering, electrical engineering, and systems engineering and aviation. We have more directions, but usually these are the typical source for my module. The organization is, I have to introduce a little bit analysis, because they have only the basics, the derivatives, integrals. They do not know much about functional analysis. Then, and PDEs, of course, is not well known. Then I introduce numerics, and because I'm using here I'm introducing here a functional analysis. My focus here is on the finite element method, and afterwards we end up with application and have this circle around to the application. So let's have a short look at the analysis. So here, as I mentioned, I give a really basic functional analysis introduction, basic concept, function space, and the calculus of variations to be able to compute the weak equations. So we have the differentiability in function spaces. Then I give an introduction to partial differential equation. Here we are I show what it is, and we make a classification, and then we have the focus on modeling for stationary diffusion processes, transient diffusion processes, and the hyperbolic equation. So this is typically the framework where I'm later on with the projects. And then, of course, from the variation and functional analysis approach behind, we use finite element methods. Here I'm introduced it in one dimension, and this I will show later on, and linear equation solvers. So once a colleague told me why to teach the students how to compute a linear system, we have LAPACK. It's not necessary. So then, yeah, I was a little bit confused because we have seen yesterday to compute the linear equation. I think it's still the problem we have. For real world application, the problem gets great, and in the end, the problem we have is to solve this equation accurately. So we have to teach how we can compute linear equation and in which structure they have. And then later on we have some practical applications also in my course script and in the exam. The software is based on Python, of course, and NetGen. So perhaps some words about the course material. Here I'm using Jupyterbook. The script, I have here the link to the script. It's a published Jupyterbook, of course, in German, because we are teaching in the bachelor's course in German. And then we have Moodle, not interesting, but one point here, because it's really hard. What the student like to have is one PDF file over the whole Jupyterbook, and this is really difficult to get. This I have to mention. So we can extract single pages without problem, but if you want to have the whole book, it's really a problem. But the nice thing is all calculations can be done by the student himself, and I think this is very important. Then, yeah, we have heard it yesterday, but it gets better and better and better. But anyway, I have a Jupyter Hub available for students who are not so familiar with installing software. So this is, I have to say, also a problem for students of computer science. I don't know what they are learning behind me, but they have problems with installing software and compiling. Yeah. So here I'm using the little Jupyter Hub, and it works quite well with pip install. So I have in the intranet of ZHW Jupyter Hub at the end for the students who are not successful in installing NGSolve. Yeah. So now, okay. So perhaps now some projects. So I've mentioned these projects are for the semester end exam. So I do not have here Jupyter notebooks, because otherwise the students have the solution, so it wouldn't be interesting for me. But we can, of course, speak about how we can use perhaps for your library also. Here the first project is for electrical engineers, mechanical engineers, and system technical engineering. So this is a mix of mechanical and electrical. We have here an ABS sensor, and this tooth plate is rotating under this magnetostatic field, and we can simulate here this rotating plate and the magnetic field which we have. So we have Maxwell's equation in 2D. So usually I keep the dimension here low to have a short computation time and not too fancy numerics behind. Anyway, we have here rotating subdomains, so I have showed them the hybrid interfaces to make such a simulation. And in the end, they have the question where they have to put, for example, a Hall sensor to have a nice signal to count this tooth under this magnet. Here.
An error, or is it? So how do they find the optimal position?
This is up to the student to hit IDs. Yeah, it depends really where do you put it for the orientation and to have a nice sinusoid signal. And there you have typically a trigger where you count this positive. Yes, yes, yeah, yeah. It's not specified in detail. So the next project is a hot air balloon. So this is the reason why I have asked you yesterday, how small can we choose our viscosity? For example, here we have a heat source and we are simulating this flux in this balloon. So we use a Boussinesq approximation and compute the rotational symmetric Navier-Stokes equation and, of course, coupled heat equation. So we have, in the end, a nonlinear coupled system. For the student, I had to scale it down, of course. It's more such a balloon, Himmelslaterne, we call it in German. It's a nice thing, but it has to be wet. So, next project. This is a project which I have handled also as an industrial application. It's a heated godet roller. It comes from the textile industry. One has to warm up some garn here on this roller. So it's a rotational symmetric geometry. We can compute the magnetic field and the temperature, magnetic field here in the upper side, and temperature field for this inducted heat source we have. So we have harmonic Maxwell equations. They have to handle also complex valued problems in an axial symmetric setting. And yeah, at the end, we are interested in the temperature distribution on this cylinder. So for the computational science students, I have here a mathematically imaging processing problem. Here we are using Ginzburg-Landau functional. I think it's also on the 2x2 IFEM collection, this functional. And so we use a time-dependent approach to compute this nonlinear boundary value problem, and we make a fast separation, and the student can also here have a look, study very nice the influence of the diffusion constant. Another well-known problem is here the membrane, so I jump it to the nonlinear elasticity. This is a problem which came from a student. He asked me, would it be possible to make a project where I have such a balcony, a beam, thank you, and where we are making optimization to have a given deformation, for example, with minimal mass and minimal stress. And so I have set up a project here where we are using a near hook as hyperelastic material model, and we make a comparison with linear elasticity theory, and this optimization is done with SciPy optimize. It's really nice. It works quite well. So here, the interesting from the student is to get machine learning together with an application, and it's a really nice application in that point. Fast computation is possible. Another point is this espresso sieve. This project came from a student. In the same time, I was thinking about it. It was funny. They had so in the autumn semester we have project work, and in the spring semester we have the bachelor work, and they studied this espresso sieve with CFX, and they want to solve it also with finite elements, and here we have Brinkmann-Forchheimer equation used to simulate this flow through this porous media, the coffee grain we have. And then they, sorry, I have no power adapter on my notebook. Then we can study the influence of porosity and the mean particle diameter, but in the end it was very interesting. What do you think is important for the flow in such a coffee sieve?
High pressure?
Yeah, pressure, high pressure, yes.
High pressure.
But on what depends high pressure? You think porosity? Other ideas?
Grain size.
Grain size, yeah.
Also the change in area.
Yeah, the change in area, it comes closer. The really point is how big are these holes in the sieve? It was, for me, it was not so clear, but afterwards, the point is how large are these holes in the coffee sieve. So not the geometry, not the grain, not the porosity. It's how good can you resolve here these outlets?
What about outflow boundary condition?
Here we have a no-slip boundary condition, and then pressure free, of course. And here we have an inlet boundary condition. Yeah, yeah. It would be a nice point to model this part. Of course, we see a multi-scale ansatz, perhaps, because in 3D it would be really hard to compute it. Yeah. So I have to go back.
We already contacted you.
So
The Italian espresso maker.
no, at the point not. So you are in Switzerland, but I don't know if they're developing the machines in Switzerland. So another very nice project, I love it. I have it also in my script, this proportional integral controller. So this is not P, this is PI, proportional integral controller, for a given room temperature. So perhaps I make it a little bit larger. So we have here this T sol, the temperature in our room we want to have. Our room is here given by a 2D cut. We have here on the right-hand side a time-dependent Dirichlet boundary condition, a heating source at the window, so I call this side window. Then we have here the boundary condition with a robin to have a flux out of the room, and we want to control this heat source And they have to combine this time-dependent parabolic equation with a PI controller. It's a very lovely project. And at the end, it's, of course, very interesting. So how many energy you are really using to have 1 or 2 degrees more in your room? It's not direct proportional, so it's really interesting. So here I have learned yesterday, now we can combine streamlines or vector fields with a scalar field also in the web GUI. So I will change this picture. It's a heat exchanger. Here we use Boussinesq approximation, and it's more or less the same as the heat balloon. Then another project, this came also from students, is a propagation of sound. They want to compute the wave equation on a GPU. They have used in their bachelor thesis a library, and in my course they have computed it with a H1 ansatz and the time-dependent wave equation, and studied the influence of boundary condition. And last but not least, they have made a comparison with a harmonic solution. So for the student, it's really not clear what is a harmonic solution at the end. So here they were able to study this quite nice. The last project I want to show here is this underfloor heating. This is a project which also came from a bachelor thesis with an industrial company. They make valves, and they are interested in modeling in a computational possible way this heat transport we have in such a pipe. And if this pipe is not a small circle, it's in this room, so we get meters, 15, 30 meter rooms, and we have such a spiral here with a fore and back flow. So here we have 2 pipes together which are coupled in the end, and so they first in the first step they had to compute this time-dependent heat convection conduction equation in 3D to get the feeling what is done here in the real world. And afterwards, that's quite interesting, we make a dimensional reduction from 3D to 2D and make such layers. So they have to compute the flow in this first layer, and afterward we make a coupling outside of this plane to the floor which we are feeling here. It works quite well. So these projects, one gets nice pictures as you can see. Yeah, you stop me if I'm too long.
2 minutes?
2 minutes, yes. So 2 minutes, perhaps one of the important point is if you are using Jupyter with in combination with NGSolve, we have to export in this static folder the web GUI JavaScript. And yeah, perhaps you have a nicer way, but I have taken it here into my presentation. So I write out this code from the web Jupyter widget, and then you are able to have this Jupyter NGSolve GUI also in a markdown file. So here I'm scrolling through a markdown file to this drawing from NGSolve. In this markdown file, you see how I introduce the finite element method with NumPy, and afterwards I show the NGSolve equation, NGSolve solution and expand it in an easily way, very illustrative in 2D. So for the students, the IDs, to show the IDs is quite nice, because from the mathematics we have the correct names here, so we are integrating grad U, grad V over the volume. Of course, we can also mix markdown files with Jupyter notebooks. So here I have an example with the Gelfand equation, and here I make some more mathematics, and we compute such a branch of solution, of lambda-dependent solution for the Gelfand equation. You can look by yourself. This Jupyter book is open, it's public on GitHub, so you can also clone it and use it for yourself. Yeah, thank you.
Thank you very much, Simon. Forget about the link, it's already linked into the material of the workshop here.
Yep,
So you find the link. Yeah.
Yeah.
Very nice, I enjoyed very much this presentation. Some questions to it? Like a teaching aspect maybe, what are you?
It's 14 weeks, 4 lessons. It's
Okay.
it's very much, so I have a problem to give all these things. Yes.
What do you think? How much time the students need to do the projects?
So yeah, this course is chosen from students which are interested in mathematics, because you don't need to choose it. It's a so-called Wahlmodul. So they are interested in mathematics, so I have not so much discussion about how many times they really spend on it. They are interested, but I always say it depends on how many lectures I have. But how long they afterwards have to work this project through, it differs very much. And I give them also my support. So I do not let it fly by themselves, so I give my support. We make meetings, and 1 week before they give me back the proposal, I give no support. So they have to look that they have the cat in the bag 1 week before. Yeah.
Simon, what is the hand-in of the students? They produce something and they
Yes,
present it?
the hand-in I have in the background. The hand-in looks like that.
A PDF?
It's a
classical PDF file?
It's a classical PDF file where I have the Bewertung, the grading. I make it quite nice. So in Switzerland, best 86, not 1, so it don't matter. And then I have this Aufgabenstellung, so the problem through the theory and.
Okay, so the question was more: you get the PDF, you grade, and then it's somewhere archived. So
Yes.
what about? You think about let students also create books like this, put it online, and let the students apply somewhere, and say, human resources finds this online, say, here's done this, and your students can present themselves very well if they also publish the books online.
Yeah, also once I had a student, he has made it as a Jupyter book, his Bericht, his report. But the point is that would take some more time to build this nice Jupyter book. So it's not for free to have a nice Jupyter book.
It takes some experience.
But it would be an idea. Perhaps one can give a template.
You have to find new projects every year if they are all published.
This is another point, of course. Yes.
Problem.
Yeah.
Problem.
Yeah.
Okay. Thank you very much, Simon.
You're welcome.